modulation. So basically, pseudo-periodic modes, as we will see, are sinus or cosinus modulated by exponential functions. So, things like this. Or constant modulating function, and so oscillations with constant amplitude, and these are periodic modes, basically. Okay. Otherwise, we have pseudo-periodic modes, which may be of this form. So, diverging or converging. So you see, you have periodic functions like sinus or cosinus modulated by, this is the modulation, in amplitude by basically exponential function. So the modulation is always of the exponential form. And the exponential again will depend, as in the case of periodic aperiodic modes, will depend on the real part of the eigenvalues. Okay. So basically, the modulation is determined by the real part of the eigenvalue, while the frequency of oscillations as we'll see, is characterized by the imaginary part of the eigenvalue. So, basically what we expect to see, this is a case with the real part of the eigenvalues equal to 0, so that the modulation is constant. Because the exponential is constant. Okay, and so the mode will oscillate only according to the imaginary part, the non-zero imaginary part. So the imaginary part determines the number of oscillations in unit time. In this case, as in the aperiodic mode, the real part of the eigenvalue is positive because in this way the modulating function, the exponential modulating function, is diverging. Okay. And again, the frequency of the oscillations will depend on the imaginary part. In the last case, the real part will be negative. Okay. So before going to the technical details, as we did in the case of aperiodic modes, we can basically imagine that the periodic or pseudo-periodic modes may be subject to similar classification of the aperiodic modes. So, for example, in this first case, we say that the pseudo-periodic mode is constant. In particular, more precisely, is periodic. So this is the case of periodic mode, where the real part is 0 of the eigenvalue. When the real part of the eigenvalue is greater than 0, is positive, we'll have a pseudo-periodic divergent mode. Okay. Divergent mode and convergent mode. Okay. So pseudo-periodic modes can be classified into constant, divergent, or convergent. Particularly when the pseudo-periodic mode is constant, we simply say that it is periodic. Okay, so let's see how to obtain model decomposition when we have only pseudo-periodic modes. Okay. Physically, for example, pseudo-periodic modes correspond to systems which oscillate. Okay, for example, an harmonic oscillator. An harmonic oscillator has this model. Okay, so this is the matrix A. The characteristic polynomial is this. So you see that we have two complex conjugate eigenvalues. Okay, in particular, lambda 1 equal to j, and lambda 2, which is equal to lambda 1 conjugate, equal to minus j. These are the solution, the roots of this polynomial. Right? So in this case, we have two imaginary eigenvalues. So they are placed in the complex plane here. J minus j. Okay. So this is exactly the case in which we have, for example, a pair of complex conjugate eigenvalues. No? In particular, imaginary, purely imaginary. Real part is 0. So as for what we said before, what we expect in this case is a periodic mode, because the real part is 0. Okay, so we expect to see pure oscillations, not amplified nor attenuated. Okay. As a matter of fact, this is the model of what we call an harmonic oscillator. This is a system which oscillates, gives pure oscillations. Okay. Its equations are this. Okay, you can also modulate the frequency of oscillations simply by parameterizing this equation in this way. So you can parameterize frequency of oscillations simply by taking this. So instead, okay, so in here we are taking omega equal to 1, and here we are taking omega positive, any number. So omega is exactly the frequency of oscillations. So you can modulate the frequency of oscillation just simply changing the model in this way. As a matter of fact, this model, if you do the same calculation as before, has eigenvalues lambda 1 j omega, lambda 2 minus j omega. So you are changing the imaginary part of the eigenvalue. And so, for what we said, you are changing the frequency of the oscillations. Okay. Okay, let's see this. So we will proceed exactly in a parallel way to the case of aperiodic modes. So this is our second case. So in this case, we will assume that the spectrum of A consists only of pairs of complex conjugate eigenvalues. Okay. Non ho visto. So, okay. Okay, for consistency, since we are considering a case in which we only have pairs of complex conjugate eigenvalues, since the dimension is n, okay, n is the number of eigenvalues, and since we have pairs, all pairs, obviously we are assuming that n is an even number, okay? So, for this reason, we represent the spectrum in this way. Okay, so basically we have n over 2 pairs of complex conjugate eigenvalues. Moreover, we are assuming that these eigenvalues are, in a very similar way to the case of real distinct eigenvalues, are pairwise distinct. So no multiple pairs. Okay. So which means that each pair, in comparison with the other pairs, will have either the real part or the imaginary part different. Okay. Okay. Moreover, we will also have a general representation of these numbers. Okay. Mi I. These are complex numbers. Okay. Now, not real, not simply real. So more general, complex number mi I with its conjugate point mi I star, and we represent this complex number with its real and imaginary part representation. Okay. In particular, we call alpha I its real part and omega I its imaginary part. Okay, so imagine that each number mi I is represented in its real and imaginary part as follows. Okay, so alpha I is the real part and omega I is the imaginary part. Okay, so accordingly, it is obvious that this means that the complex conjugate Okay. So let's just do what we did in the case of a periodic modes. So these are the distinct pairs with eigenvalues. Let's find eigenvectors. So we imagine a very similar situation to the case of a periodic modes. We will see, however, you see that actually here it's a slightly different situation, because while in the case of real distinct eigenvalues, for each eigenvalue we have one eigenvector. Okay. Here we have a pair of eigenvalues, complex conjugate eigenvalues. Okay. So what we have here in general is that instead of one single eigenvector associated to the pair of eigenvalues mi I star, we have a pair of eigenvectors. In particular, one eigenvector and its complex conjugate counterpart. Okay. Basically, this is a simple result which comes from algebra. So when you have a pair of eigenvalues, complex conjugate eigenvalues, you can associate to this pair a pair of eigenvectors, which are complex conjugate. Okay? So this is a general result of algebra. Okay, so what we expect here is to associate with each pair of eigenvalues, complex conjugate eigenvalues, one pair of complex conjugate eigenvectors, right eigenvectors. Okay. However, if mathematically this is completely satisfactory, we take these eigenvectors, complex or not, it's not important. But if we if you imagine that after we'll use, as we did in the case of a periodic mode, we'll use these eigenvectors as a basis, then altogether as a basis for the space. So if we have complex eigenvectors, we have a complex basis. So we cannot represent then clearly the solution with natural modes, which has a physical meaning, basically. Because in the complex base, we will get something which is complex. Okay, so not real, not physically meaningful. Yeah. So for this reason, we look for a different type of base. In particular, again, algebra is matrix algebra is helping us out from this situation. And instead of considering a base formed by each eigenvector and its conjugate counterpart, we'll consider the real part and the imaginary part of each eigenvector. Okay. So matrix algebra says or proves that by doing this we obtain another basis. But now the basis is real, because we are considering not the pair of complex conjugate eigenvectors, but we consider one eigenvector and take its real and imaginary part, which are real vectors. So the final basis will be given by the real and imaginary part of each eigenvector. Okay? So again, for each eigenvalue, in particular, we will consider one of the two, and we consider mi. Okay? So we associate to mi one eigenvector, which will be complex. Okay? So you will find this eigenvector exactly in the same way, according to the definition. The only difference is that in this case, mi is complex. Okay. Okay, so you have simply to solve another, once again, an homogeneous system. Now, the system has complex coefficients, so the solution will be complex. Okay, so let's call our eigenvector Qi. Okay. So we will, as always, calculate an eigenvector Qi associated to mu I. Okay. Now this Qi, we will see this also from the examples next time. As we said, in general, is a complex vector because we are obtaining this solution Qi from a complex system of equations. Okay, so by this reason we represent Qi as in the same form as mu I, with its real and imaginary part, which now I remember are vectors, because Qi is a complex vector, so we represent this vector, this complex vector in its real vector and imaginary vector part. Okay, let's call the real part Vi and the imaginary part Wi. Okay, so this. So now the big difference with respect to the aperiodic mode case, the case of aperiodic modes, in that case we have the different real eigenvalues and we take as basis of Rn the corresponding eigenvectors. Here, as I said before, actually we have two choices. We may consider Q1 star and Qn over 2 star, so the complex conjugate eigenvectors, okay? And this, however, is a base of Cn, okay? But we want a base of Rn. Our space is something physical, so not imaginary. Okay, so for this reason, instead of taking by pairs qi star, we will take real and imaginary part of qi. So v1 w1 and vn over 2 w vn over 2. So the real and imaginary part of each q1 qn over 2. And so this is a base of Rn. This is a result, obviously, of matrix algebra. We are not proving this yet. Okay. So we are obtaining a base by doing this. Basis by doing this. Okay. So if since we want to maintain a real representation or real decomposition of our solution, we choose the second option, and so that we have the base of Rn. Okay, so with this base, exactly tomorrow, we'll do this tomorrow, we'll basically do the same thing we did for the case of real distinct eigenvalues. Okay, so we will use this as our preferred basis. Okay, and I want to anticipate this. What will happen is that instead of having one single direction, remember the eigenvector zi, in the case of a periodic mode, and the periodic mode is moving along this single direction. Okay. The pseudo-periodic mode will move on a plane, which is exactly the plane spanned by VI, WI. So the big difference is that while an aperiodic mode is moving on a line, a pseudo-periodic mode is moving on a plane. Exactly the plane spanned by the real and imaginary part of an eigenvector associated to the eigenvalue mi. Okay, for this reason, what you observe instead of a linear motion, you can observe oscillating motions. So like this, on the plane. Or, so you observe either circles, periodic modes, or helicoidal behaviors. Okay, or diverging helicoidal behaviors or converging helicoidal. Okay. So this is what you observe in this case. Okay, that's it.